So part 2 of this phase change conversation is going to start us off with some examples. So this probably looks a little familiar. When we did the thermo unit, we did some problems like this. So the specific heat of gallium is presented there. How much energy will it take to raise the temperature of 20 grams of gallium from minus 25 to positive 25? We're assuming that since you don't have any other information, that it is staying in the state that it is. In this case, it's staying as a solid. So what do we need to do? We need to use Q equals mc delta T. 20 grams of material times the specific heat times the temp change. Notice that it's going from minus 25 to positive 25, so that's a total of 50 degrees. Gives you your value. Second idea, now we're going to take a look at a little bit more work involved. So you've got a liquid that has a specific heat, liquid water has a specific heat of 4.184 joules per gram degree Celsius, and the heat of fusion, so fusion, remember, is from solid to liquid or liquid to solid, 6.02 kilojoules per mole. Determine the energy required to take water from ice at 0 degrees to a liquid at 75 degrees. So we've got to do two things. We have to take that ice and melt it at 0 degrees, and then we have to take that liquid water and raise it from 0 to 75. So there's two tasks that we have to do. So the total energy is going to be the sum of those two tasks. You've got to melt the ice, so 500 grams times the specific heat is in kilojoules per mole, so we've got to convert the grams into moles. And then you have to add to that the energy from the specific heat from the temp change from 0 to 75 of the liquid water. So still 500 grams, specific heat of water, and the temp change is 75 degrees Celsius. Units got to cancel out. Appropriately, this is in kilojoules, this is only in joules, so we got to convert one to the other. I always convert to kilojoules. So now I can add them together, and the total amount of energy required is 324.1 kilojoules. For complicated heating and cooling curves, it might be useful to actually draw your own heating and cooling curve. So if you have 5 sections, if you have 4, if you have 3, whatever it takes. So here's an example where you've got a whole lot of change going on. So all of these constants are available to you, as well as melting points and boiling points. That lets you know where the plateaus are. We want to draw a heating curve and then calculate the energy in order to go from 25 degrees, which is below the melting point. So we have solid copper. We're going to take it up to 3000, which is above the boiling point, so we've got a gas. So we have to traverse all 5 sections of that heating curve. So you draw the curve, 25 to 1030, it's a solid, then it melts, 1030, 1083, 1083 to 2567, it's a liquid, we're heating it up. Then we're going to vaporize it. Then we're going to raise that copper gas up to 3000 degrees. So first task, Q equals mc delta T of just the solid. So here's the specific heat of the solid. 100 grams, temperature change is that. Melt it using heat of fusion. Raise the temperature of the liquid using the specific heat of the liquid. Change it from a liquid to a gas using heat of vaporization. And finally, raise the temperature of the gas from 2567 to 3000. So total energy, we've got to add these all up, and notice I've already converted everything into kilojoules. Total energy winds up being 13,595 kilojoules. All right, the other kind of diagram that we actually haven't seen yet is called a phase diagram. And so it's just a graphic way of summarizing temperature and pressure conditions of a substance. So it shows what state it's in and so forth. So couple areas to take a look at. The line represents at what temperature and pressure you have that conversion. So notice that you have the solid to the far left, you have the gas to the far right, and then the liquid is in the center. So sublimation, where you're going back and forth between the solid and the gas, melting or freezing as you're going back and forth between the solid and the liquid, vaporizing or condensing, where you're going back and forth between the gas and the liquid. There's a couple of other things to note. You've got something called the triple point here, and you can see that at this triple point, you technically have all three states simultaneously. So this is a pretty cool position. You also have something called the critical point. We saw critical temperature and critical pressure before. So the critical point is the point at which you can't take a liquid, you can't take a gas and condense it under any pressure whatsoever and make it a liquid past that critical point, past that temperature. So you have a gas that no matter how much I condense it, there's so much energy involved that I can't get it back into a liquid state. So again, take notice that on the phase diagram, the axes are temperature and pressure. All three phases are shown. You can see the melting points and the boiling points based upon the pressure. You see the triple point, again, where all three substances are simultaneously there. Here's just for reference, water's triple point. Notice that the temperature needs to be really, really, really low, and you need a very low pressure. So in order to have a triple point, that's unrealistic for us to experience. Critical point is, again, beyond the critical point. The gas and the liquid kind of becomes indistinguishable. You can't condense the gas any more than, or you can't pressurize the gas any way in order to get it back into a liquid. Here, another example, the critical point for water is pretty high pressure. And a reasonably high temperature. That's not too bad, actually. A couple of other things. The angle of the lines between the solid and liquid phase gives you the relationship between density. For example, the line for water actually goes from, well, it starts off at the triple point, and then it moves back as you increase the temperature. I'm sorry, as you increase the pressure. So that's letting you know that the density of the solid is actually lower than the density of the liquid. The curve from the triple point to the critical point gives you some information about the vapor pressure as well. So here's an example of CO2, so we'll be able to point that out a little bit better. So notice that with CO2, you have the line going, well, almost vertical. But with water, because the density of solid is less than the density of liquid, you actually see that line go like this. So that's what I was trying to point out on that last slide. So here is normal boiling point, pressure of 1 atm. So CO2 goes from a solid to a gas. It's not technically boiling point. Goes from a solid to a gas at minus 78 degrees Celsius. So there is no normal boiling point. What else? Here's the triple point. A pressure of about 5 atmospheres, a temperature well below zero, however. Critical temperature is 31.1 degrees Celsius, but a reasonably high pressure, 73 atms. So sublimation, how can this explain sublimation? So at normal atmospheric pressure, it goes from solid to gas. It doesn't go to liquid. So this is why sublimation happens with solid CO2. Okay, so here is another graph. Let's do a little practice. If I want to know what the approximate triple point is, it's right there. So what's the triple point? About what, 8.5, 8 to 8.5. It's a very thick line. ATMs and about 40 degrees Celsius. Normal boiling point, so at 1 ATM, normal boiling point is going to be negative something. So what is that, about negative 30, 35, something like that. Is it really boiling? Again, CO2, like CO2, it's going from the solid phase here to the gaseous phase here. So it's not really boiling, it's subliming at 1 ATM. And finally, what would the state be at 10 ATM and 50 degrees? 10 ATM, 50 degrees. We've got a liquid, barely a liquid, just above its melting point there. All right, so that's how you use that graph. Okay, so that should be the last slide to take a look at. So go ahead and read those sections in the book, and then we'll work on problems to follow.